Hi, welcome to Unit 3.3 Thermodynamics. This is part 1.1 of part 1.2 and then later part 2. So there's sort of three parts to this. In part 1.1, we're just going to do a quick review. So as you know in this unit, what we've been focusing on is thermodynamics. And thermodynamics is one of the two key things that a chemist wants to or needs to understand about chemical reactions in order to fully understand them and be able to manipulate the reactions to do what you want them to do. The other being kinetics, which is the study of reaction rates. In thermodynamics, what we focus on is how far a reaction proceeds to completion and how much energy is lost or gained during that process. There are four laws of thermodynamics. We, in 3.1, focus on the first and the 0th law, and now we're going to even focusing on the second law of thermodynamics in 3.2, and we're going to sort of continue talking about themes that are related to that in 3.3. So let's just quickly recap 3.2. What we covered in 3.2 is that chemical and physical changes are motivated by the desire to get to a lower energy state. And we use the idea of a ball rolling down the hill. At the top of the hill, it has high potential energy, and at the bottom, it has low potential energy. And since it stopped moving, no kinetic energy. So it's the lowest energy state. We also learned that a spontaneous process is one that occurs without any outside help, and it's not necessarily fast, and we know something is spontaneous because delta G is less than 0. And the reason why the first and second point sort of matches up is because reactions tend to go towards the lowest energy state spontaneously, meaning you don't need to move the ball down the hill. It will roll down the hill on its own. It will roll down the hill spontaneously because it's getting to a lower energy state. We also learn about cases where a reaction becomes more spontaneous, and there are two cases. Either the reaction can release heat, or which is a delta H being negative, or it can increase disorder, which is delta S entropy being positive. So in both cases, we can increase the spontaneity. We also learned that we can use the delta G equals delta H minus T delta S equation to predict when a reaction is spontaneous based on the sign of delta H and delta S. And here's sort of the work for that. Remember that in some cases, the reaction is always spontaneous. Some cases, it will never be spontaneous. In some cases, it's spontaneous at high or low temperatures. And all of that depends on the sign of delta H and delta S. As we mentioned before, when delta G is negative, it's spontaneous. We also learned what delta G means at other values or signs. So delta G equals 0, that's at equilibrium. And when delta G is greater than 0, that means it's non-spontaneous. Finally, we looked at standard conditions, and I think you'll need to add this to your notes because it may not be there. We looked at standard conditions, so the amount would be 1 mole, or concentration 1 molar, or pressure 1 atmosphere, and that means that everything in that reaction is at those values. And the one thing we're going to take out is this last bullet point here. Sorry about that. Okay, so just take that out. We also learned that most reactions do not take place under standard conditions, so we had to sort of figure out what to do when they are not taking place under standard conditions. And what do I mean by what to do? Like, you may need to multiply it by 2 because you're doubling the moles or something like that. Now, so let's get into sort of this idea of Gibbs free energy. We talked about this a little bit before in the 3.2 packet, but I also want to recap this in this video here. Let's begin with some history. So the Gibbs behind Gibbs free energy is Josiah Willard Gibbs, and what he did was he performed research. The aim was to make a more efficient steam engine, and steam engines are the precursor to the combustion engines that we use in our vehicles now. And so his studies and his theories have been used to help create more efficient combustion engines. So one can say he was, and this is him right here, was one of the original Fast and Furious. He was trying to make a more fast and furious steam engine, and so a lot of those innovations are the result of his work. So we talked about Gibbs free energy before as being representing the maximum amount of work, and work is the energy needed to move something. So in a combustion engine, what happens is gasoline is ignited, and once it's ignited, it combusts. And that combustion reaction results in an increase in pressure and the release of heat as well. And that sort of thing moves the piston inside the engine up and down. And that's actually doing work. By moving the piston, the combustion reaction is doing work. That work then ultimately leads to the car doing work, which is moving us around. So what Gibbs free energy is measuring, what's the maximum amount of work that combustion process can do? We are going to lose some of the ability of the system to do work to all sorts of things, but Gibbs is measuring the maximum amount. If everything went well, there was no friction, this is the maximum amount of work it can do. Okay, so when we focus on the signs of delta G in terms of work, there are a couple things we're looking at. Either the system is going to do work or the system will have work done on it by the surroundings. When delta G is less than 0, when it's negative, the system will do work. And we can see that in this chemical reaction. We're told that the delta H of this reaction is negative, so that's a good sign that it's going to be spontaneous. And delta S, we can actually predict that it's positive. Let's see how we can predict that. We have 2 moles of gas on the reactant side and 3 moles on the product side. So we're increasing the disorder by increasing the number of moles. And so we know delta S is going to be positive. If delta H is negative and delta S is positive, then delta G has to be negative. It's always negative. So we know this will be a spontaneous process. The system will do work. So what happens here? This is a reaction where NO2 decomposes, and in decomposing it releases some heat, so like a little explosion goes off, and that's going to cause the piston to sort of raise or lift up. And so the system is doing the work because through that reaction, when that reaction sort of releases that heat and the reaction expands because you're going from 2 moles to 3 moles of gases, all of that helps to lift the piston up. And by lifting the piston up, the system itself is doing work. In the case where the system has work done on it by the surroundings here, this will be sort of the reverse reaction. Let's say we had the reverse reaction happen. So in this case, since it's a reverse, delta H is going to be the same value but opposite sign. So it's going to be positive 33. So this is an endothermic reaction. And the delta S is going to be negative. And again, we can predict that because we're going from 3 moles of gas to 2 moles. So we're decreasing the disorder. So delta S is negative. So let's say we start off here with that piston at the top there, and then this reaction takes place, which because we have fewer moles of gas, it's sort of it's doing the opposite of expanding. It's contracting. The system is contracting. And also because the temperature is going to get cooler since we are absorbing heat from the surroundings, we're going to get like a slower movement of particles. And then so here we have the piston will go down and the system has work done on it by the piston. All right. So that's just sort of to highlight what we mean by work being done. This becomes more relevant and makes more sense when we get to gases, but it's good to sort of start seeing this sort of thing now. All right, so that's the end of part 1.1. It's just sort of a recap. We're going to move into 1.2.